All right. For our final project, we decided to model cancer growth with agent-based modeling. Computational modeling, as used in this project, offers a valuable tool for identifying areas of interest for further investigation. While modeling cannot replace laboratory research, it can significantly narrow the domain of possibilities, helping to prioritize experiments and optimize research efforts. While the search for a general cure for cancer is ongoing, there are many different avenues to inhibit the proliferation of mutated cells, such as radiation treatment and cell transplants. However, our group chose to model chemotherapy, which is a common method of treatment for numerous cancer types and involves administering pharmaceuticals that are designed to eradicate rapidly dividing cells, such as those that are cancerous. So our main lens is experimenting with chemotherapy and understanding how this affects the tumor. The key that we must also, of course, maintain is the balance in computational efficiency while being as realistic as possible. With humans having trillions of cells in the body, each containing complicated dynamics, simulating all these cells can be quite computationally difficult. This leads to our key model assumptions. While numerous assumptions were made, there were a few select assumptions that were made that significantly simplified the model. First off, we modeled the vasculature with a linearly decreasing concentration gradient of chemo, nutrients, and oxygen. Second, our mechanism for cell death is a simple metric of damage, which is inflicted to the cell as it mutates or absorbs chemotherapy. Thus, explicit pathways such as apoptosis or immune responses are not encoded. Another major assumption was modeling healthy cells with one generic cell type, rather than implementing various cell types that can be found throughout the body. While this significantly decreases the complexity of the dynamics, some accuracy is sacrificed as certain cellular behaviors are lost.
Our model was coded in Python using the implementation of 3 classes. First is the cell class, which encodes information about each cell. This includes cell oxygen, nutrient, and chemotherapy concentrations, age, and stage of the cell cycle. Additional attributes are included for traits such as the ability to invade neighbors, probability to mutate, and the resistance to death. These are all known mechanisms of cancer and are set to higher default values than healthy cells when cancer cells are initialized. Each cell can progress through each stage of the cell cycle when certain criteria are met. And the second class that we implemented is the extracellular matrix, which encodes the concentration of extracellular oxygen, nutrients, and chemotherapy. Vasculature is also encoded in this class, and in this model is a simple column of tissue or simple column of vasculature in the center of the tissue. The tissue class combines both the cell class and the extracellular matrix class and provides methods for simulation and updating the concentrations of the extracellular matrix. Further, the tissue class uses methods to update all of the cells randomly or in a random order and deliver chemotherapy on a scheduled timeline. For our actual experiment, our research question was how frequently and at what dosage should chemotherapy be administered to optimize treatment outcomes for cancer patients. We conducted 3 trials for each condition we simulated using high and low chemotherapy concentrations with treatment intervals of either 14 or 28 days. Each simulation runs for 180 days. During the first 60 days, the cancer is allowed to grow and no chemotherapy is applied. Data was collected over the duration of each trial at 12-hour intervals.
Diving into the results of our model, we begin looking at the high concentration case. For each case, we ran the experiment 3 times. In looking at the results of both timings, both the video simulation of the cancer cells and the plot of the cell count, We see that the darker blue line represents the average results of the 3 trials, while the shaded banded region shows the standard deviation of the cancer cell counts. In the video simulation, the pinkish red cells are the healthy cells, the black cells are the dead or vacant cell spots, and the brown cells are the tumor. As the chemo isn't applied until day 60, we see that in both cases, every 14 days versus every 28 days, that the peak number of cells occurs at or just after day 60. This slight delay can occur as it takes 12 to 24 hours for a cell to die. Comparing the results between the 14 and 28-day administration of chemo, we see a far quicker dying off, killing of cancer cells when the chemo is applied more frequently. This more frequent administration has the key negative side effect of killing healthy cells. Remembering, those are the pink ones. This can be seen with more pronounced pulses of black cells, which we'll see momentarily contrast with the lower concentration chemo application. Lastly, as we'd expect, the more time goes on, the more rounds of chemo are applied, and the tumor is eventually eliminated, which results at the 125-day mark in both cases. Next slide. Continuing, we look at the same application schedules, so 14 and 28 days, but with a low concentration of chemo. When the low concentration of chemo is applied at the more frequent interval, the 14-day case, we see a more even distribution of cancer cell counts, with the cancer cells being eliminated in a far smoother, nearly exponential decay-like shape. Interestingly, like the previous 2 high concentration cases, the cancer is completely eliminated around the 125-day mark. But contrastingly, when the low dosage of chemo is applied at the less frequent intervals, the 28-day case, the tumor size shrinks, but it never is completely eliminated and stabilizes at about 3/4 of its maximum size with respect to cell count. This is interesting and has some implications for treatment and management that we'll discuss in our paper. Lastly, like we alluded to earlier, the simulation video showed there is a far less pronounced killing of healthy cells with a lower concentration of chemo. Next slide. So, tying this all together, the key question with treatment is often how much chemo and when to administer it. We find that the low concentration at a more frequent interval is best as it eliminates the cancer in the same time frame as the higher dosages while doing less harm to the healthy cells. This is especially important to us as while we don't explicitly account for it in our model, healthy cells are not all equal. After all, killing cardiac tissue could be very problematic. Overall, our results are not entirely surprising. In fact, there is a paper that shows exactly the same thing, which the image on the slide shows the title of. Next slide. In conclusion, like all models, our model has some limitations and simplifications, but it demonstrates the utility of computational approaches in cancer research. By focusing on the most sensitive parameters and making these parameters easily tunable by experienced doctors, our model can suggest promising experimental directions and treatment strategies, ultimately contributing to the broader effort of understanding and combating cancer. Thank you.